This is a talk about CheckPlease, a new repository we're releasing. It's on implant security, which we believe to be the future of sandbox detection. My name is Brandon Arvanaghi. I'm an associate consultant at Mandiant, and while I've been there, I guess Chris added to my slide a little bit. I've been doing red teaming, some reverse engineering, and tool development. And before PowerShell reverse engineering. And before that, I studied computer science at Vanderbilt University. Just go to the next one.
My name is Chris Truncer. I'm a previous sysadmin turned red teamer. I'm in charge of Mandiant's West Coast for all of our red team. And I'm an open source developer. I work on a variety of different projects that I like to work on in my spare time.
So let's start with the pop quiz. We've evolved from one answer to the other. That's your hint. Which is more effective at stopping malicious applications from executing? Is it blacklisting or whitelisting? Anyone can raise their hand and answer. Yes. Excellent answer. I couldn't have said it better myself. Application whitelisting is how we've evolved. Rather than trying to figure out every single malicious application that we don't want to run, we've started to whitelist those that we do want to run. We disallow everything else, and we're seeing this new system integrated into Windows now with AppLocker and different technologies as well. Remember I said that. It's going to be an important point. Let's pivot to sandbox detection. A sandbox is a virtual environment designed to simulate a real computer that can analyze malware behavior. It's for dynamic analysis. Most of you know this already. Malware does not want to be analyzed, so when it thinks that it's inside of a sandbox, it'll act benign, like a calculator. The old thinking when it came to sandbox detection was that sandboxes look and feel a certain way. So let's specifically check to see if we're in a sandbox. And if we are in a sandbox, we'll act benign. Things that could indicate a sandbox are registry keys, values, MAC addresses, limited RAM size, etc. But I want you all to think about this. We are specifically looking for sandboxes. We are specifically looking for a specific kind of system to not run on. What does that sound like to you? Sandbox detection is a form of blacklisting, and that is the problem. When you blacklist, you run into problems because you can't predict what every single sandbox looks like. We've been doing this wrong, in our opinion, for a long time. And now let's think. Why do we write sandbox detection modules in the first place? Why do we add them to our code? Why do we add, if we're in a sandbox, let's not run? Is it because we're curious about what sandboxes look like? Is it because we care about being in a sandbox specifically? I don't think so. I think there's a greater point here that we're missing. We want our malware to run where we expect. That is why we check for sandboxes in the first place. It's got nothing to do with the sandbox. A sandbox is just another place that it could be running that we don't want it to run. In general, we want our malware to run where we expect. And avoiding sandboxes is a byproduct of that. That is not our goal when delivering a payload, to look for sandboxes. This is not a scavenger hunt. We just want our malware to run where we expect. Implant security is how you can do that. By securing your implant, you can know exactly where and how and the context in which your malware runs. Sandbox detection is a subset of that. So what is implant security? It means securing your implant so that it doesn't run unless, for example, the MAC address is as you expect, unless the username is what you expect, unless the host name is what you expect, the domain, etc. And if that's the case, if you're only running where all these conditions are met, you're also not going to run in a sandbox. You don't need to specifically look after a sandbox in the first place. That's blacklisting. Let's whitelist our payloads. Let's whitelist the systems and the users we target. That is the future, in our opinion, of sandbox detection. So here's kind of the workflow to get to this point. Your initial access into the domain, it's difficult to target your payload. It's difficult to have a super secure implant. But people get in one way or another, right? One of the first things we do on our engagements, before we just randomly dump creds, is we import PowerView and just exfiltrate data about the domain. So that's usernames, that's host names, that's phone numbers, things that are useful. From then on, anytime we use a payload, it can be targeted. We have the user's username. We have the host name. We can make a profile about how many processor systems on that domain have. what kind of registry sizes, all sorts of little tidbits of information to protect our payload. If we ever run a payload again, it should be targeted. It will be targeted. This way it doesn't just run out there anywhere. Some malware analyst at this big company can just look at it and say, oh, it runs perfectly on my computer, it's malware. You don't need to do that anymore. You target your payload to where you want it to run. So let's discuss some of the problems with purely trying to identify a sandbox, not just securing your implant. The problem, number one, is that you're not as smart as you think you are. It is hard enough to figure out why your payload won't run. Who here has had a problem where their payload didn't run on a system and they couldn't figure out why? Okay, good. Everyone's raising their hand. I know you can't see it at home, but everyone just raised their hand. Yeah. Sometimes it's the AV's fault. Sometimes it's the RAT you're using. Sometimes it's because of whitelisting. But it takes a long time. On one of our engagements, the client had PowerShell injection. That was, they protected against that. They wouldn't let PowerShell.exe run when shellcode was injected directly into it. And we had no way of knowing that. We had to debug for 2 days as to why our payloads weren't calling back. It's hard enough. So adding this tic-tac little sandbox detection module, it's going to make it even harder to figure out why your payload's not running. Number two, VMs. VMs used to be a really cool idea. You know, the computer is inside the computer. It's like a strange concept, right? But today, VMs are used in day-to-day functionality. Sandboxes look like VMs because they are often VMs. And by avoiding VMs, avoiding VM registry keys, registry names, MAC addresses, you're really avoiding a critical asset that a lot of companies use today. We want to target VMs now. So if we're avoiding a sandbox, we're also avoiding VMs most of the time. We want VMs. That's how we can get more access. So don't just look to see if you're a VM and say it's a sandbox. Let's get out of here. That's another problem with pure sandbox detection. Number three, sandboxes look like legacy systems. What are some characteristics of sandboxes or VMs, right? Small amount of RAM, small disk size, etc. I think this is like a Cuckoo Sandbox right there. It's a picture. But the issue with that is that legacy systems are often some of the easiest and most effective at targeting. A lot of the new antivirus don't even run on the old systems. But you can get persistence on those systems, and it's really nice. But they look like a sandbox because they're old, they're outdated, they don't have a lot of good specs on them. And you're going to miss out on all these systems if you add some sort of pure am I in a VM check in your payload. Anti-VM. Sandboxes are looking for your anti-VM measures. How many more antis do you want? Seriously, this is a game of cat and mouse. I mean, we all signed up to be in the security industry. That's fair. We're all playing cat and mouse. But you're just diving headfirst by adding a sandbox detection check. You think about what happened with WannaCry. It was a check to a URL that didn't exist, right? And some 22-year-old bought that domain, and because of that, the entire kill switch worked across every single WannaCry instance. There's problems with that. That payload was working perfectly until that malware author got cute and added a sandbox detection check that blew up in his face. Let's talk about our repository now. It's an implant security repository. What we've seen is that implant security modules or sandbox detection checks that we've read on articles or blogs, they're always discussed at a high level, very rarely ever implemented. Oh, malware authors are doing this new technique. It's very innovative. Let me tell you about it, right? Or just written in C if it is written at all. But payload deliverance is growing in non-C languages. Python. There was a talk about Go reversing yesterday. It was a good talk. PowerShell, Perl, Ruby. Let's make a repository, a centralized one, where every single module is implemented in all these languages. So we started with C. We went to C#, PowerShell, Python, Go, Ruby, and Perl. We're not fans of Perl. This is what part of the repository looks like. You have it broken down by the kind of implant security or sandbox check, and you can break it down even further. So we have disk size here, minimum number of running processes, USB drives ever mounted, things that you can create a profile about your domain with. When you break into one of them, you'll have the different modules in all the different languages. So let's talk about why sandboxes can't just go follow all these paths. Say you have a username check, right? Don't run unless this is the username. It's a design decision for sandboxes not to follow every single path that it could follow, not to follow every single if branch. The reason is because we don't have the computing power to follow every single path. If a sandbox follows some path that could never exist, if I put in if username is ZYXWTUV, whatever, the sandbox won't follow it because if I sent it on some goose chase, solve traveling salesperson problem, we'd run out of resources on that computer. The sandbox is rendered useless. So sandboxes have to follow the normal path of execution. Sandboxes will only follow what the code says to follow. They don't typically break out into all these different checks. That's why implant security is effective against dynamic analysis right now. So let's talk about some of these modules. When you deliver a payload, you should know what the parent process of that payload is. If you're delivering a Word macro, for example, the parent process might be WinWord, but it won't be cmd.exe, right? If it's a PDF document, an HCA application, any of that, you should know how your payload's getting delivered on that system. So why would you allow your payload to run if it wasn't being delivered how you expect it to? There's no reason you should. And that's an easy way to get in trouble or get caught by a company. Now, most languages allow you to find the PPID of the process that you're in. That's the parent process ID. Because in Windows, that's actually part of the PEB, which has information about the process and its parent process. If you use that parent process ID from your payload, you can do a query, just querying all the processes running on that system. Check that parent process ID and look which process name corresponds to it. And if the process name is not how you expect, this is the Python implementation, then don't proceed. But in this one, you can see we have OS get PPID, and you do a WMI query to get the string name of that. In this case, we're looking for Firefox. It's just the basic hard-coded value I put in. And if it's not as expected, you don't proceed. The malware doesn't execute. But if it is Firefox, if it did come from Firefox, then you proceed.
Just as a heads up, in case these slides are a little bit tiny or harder to see, Brandon will also be tweeting these out for review. So we realize it may be a little hard right now, but you'll be able to download this and see them.
Right. Again, we showed all the different languages we implemented these in. So I just wanted to show you again in PowerShell how it will look a little differently. This is another WMI query where you can query the parent process ID to see the corresponding process name and check it against the value you expect. As you can see, we implemented all these modules in our repository to accept a command line argument. So if you want to play with it on your own, just in your own environment, you just pass it on the command line. You say, I want this parent process ID to have this string name. And if it doesn't, don't run. But we'll talk about how you can port it over to your payloads in a second. Now Chris will talk about sleeping.
All right. So this is actually kind of one of my favorite modules that we've worked on where, again, like Brandon mentioned, we're not here trying to purely do sandbox evasion, but because we care more about the problem of delivering our payloads, having that code run exactly where we want it to run and minimize its ability to run anywhere else. Although, like he did mention, sandbox evasion is a part of that. So one of the things that a lot of people try to do when they're going to be trying to avoid a sandbox is they're going to add like basic sleeps, right? Like this is kind of almost sandbox evasion 101. So you can assume, or most people would reasonably assume, that if a sandbox is going to run your code, it's only going to run it for what, maybe 2 minutes and try to observe any action that that piece of malware or program takes. It's not going to sit there forever. So if we can make our code sleep for about an hour, we're going to beat this system, right? Well, that's not actually obviously how it works. Sandbox developers obviously also know that this is just a simple trick that any malware author is going to try to write to do. And so what they do is they look for these sleep calls in your code, and they basically hook that function and fast forward through it. So you may tell your malware, your piece of code, whatever it is that you wrote, to actually sleep for 30 minutes, sleep for 2 hours, whatever that amount of time is, and it's actually just going immediately to the next line because it's not actually sitting there for that long. So the next question is, how can this be beaten if we want to try to add this functionality in, but basically not get caught by a sandbox. Well, the way that we tried to solve this is we're outsourcing time requests to an NTP server. So we've added code, and we'll show a demo of it in just a second, or a sample of the code base, where the first thing that our code will do if we want to perform this check is make a request for the current time against an NTP server. Once we do that, we'll try to sleep for the requested amount of time that we want, 30 minutes, 5 minutes, however long it is. And then after that point, we make another request to an NTP server. Basically, at that point, we're doing a comparison of the time responses that we get back from the NTP servers. Are they actually sleeping for 30 minutes, 60 minutes, or is it really basically like 1 second right after another? If that's the case, then we can, if it didn't sleep for 30 seconds or 10 hours, however long we want it, we can assume reasonably that we're probably in a sandbox or in some weird environment that's not acting completely normal, and so we don't want our code to run in that. If it is, then let's actually execute our code. An alternative option that we are adding in is, instead of making, the problem with that first issue is you're making an NTP request. Anyone that's actually looking at dynamic behavior of your malware is going to be seeing that there's a UDP request going out there, we're talking to an NTP server, and something's going on. Well, let's just also recreate that functionality inside a program that may take a certain amount of time. So let's say it's factoring certain prime values. Let's just say we can do, some sort of other math activity that is going to take maybe half a second or a second to complete. Well, if we can reasonably start figuring out, okay, this function is going to take about 5 seconds to complete or half a second, you can just iterate over that function, obviously, as many times as you'd like, and kind of remove this network dependency for a check to occur, or for a network request to occur in your payload. And so here's a basic example in Python where right here we're just basically doing a request, reaching out to uspool@ntp.org, gathering that data, or gathering the current time, trying to perform a sleep, making a second request, and then down here we're actually trying to figure out, is there a difference between these two times? And so essentially, if there is a difference and the difference is what we expect it should be, then our malware should run, or our code that we're trying to protect should run. If not, then become a calculator. Next up, so we're kind of going to talk about encryption when it comes for trying to protect our implants. One thing that I would argue and want to state is if your malware gets to a point where it's in the hands of a skilled reverse engineer, this stuff alone is not going to beat that. So this is not designed to beat anyone that knows what they're doing. What we're looking to beat is kind of quick automated analysis by different tools out there that may be AV on a product, it may be sandboxes that it's running in, just something that makes our code not look like malware through a quick observation. In the event, that, obviously, again, that it's getting actually analyzed, then that's a different issue. And that's not what we're trying to solve. So one thing that we want to do is try to start adding basic encryption to payloads. So this is saying, hey, what if I want to dynamically draw indicators from the host system that my code is running on? So if we know ahead of time that if we want to compromise system A, and system A is part of whatever domain, it has a MAC address of this value, we can basically generate a piece of malware on our side and encrypt all of that data using that information. So MAC address, username, host name, domain, whatever it is. Then when this payload runs, at runtime, it pulls all that information off of the system that it's running on and concatenates that information back in a repeatable manner to generate a key for the system it's on. And so what we would do is try, okay, does this key match this encrypted data? Can I actually decrypt and run my original code? If so, then assume I'm on the system that I want to be on, that I'm targeting. If I'm not able to do that, then it's probably on a different system again. A great example of that out there right now, there is a tool that does very similar work. It's called Ebola. Josh Pitts is one of the developers of this. This works really well against a bunch of antiviruses actually that claim to do a lot of machine learning Silence is one of them that this will specifically target and bypass. So it's a really solid tool, and I also recommend looking at this. All right, so we have a different module also in CheckPlease called delay analysis. So has anyone here ever worked or seen or used the tool Hyperion? Awesome. So I think I talked about this. Okay. Hyperion is a really kind of cool concept that we basically rewrote in these languages that we're supporting. What Hyperion does is it's a compiled binary. You put it on your system. You give it a program. So this could be, again, your malware. It could be anything you want. It doesn't matter. You give it to that, and it all of a sudden just outputs an encrypted file. Well, this file is your original program that you gave it that's encrypted. The problem is there is no decryption key stored inside this file. So the way that this tool works is every time it runs, it brute forces itself. So it's trying every single key, and the way that it does it is through an artificially constrained key space. So let's just say, and I'll show our implementation of this, but if you have a 32-character AES key, 25 characters may be just random letters, numbers, symbols, whatever it is, and the last 7 may only be digits or may only be letters. And what you can do is programmatically iterate over all of those numbers or letters or whatever it is, and actually just attempt to brute force yourself until you find your actual key to decrypt your code. So let's recreate this. I think we'll do a quick demo in a second, but delay analysis is this tool that's written in Python. Basically, you give it the source code. So we're not working at a compiled binary level. We're looking at your original source code before you compile it. You basically just provide the language that your code is developed in, and it'll output encrypted code in that format. So, and I'll show you what this actually looks like when we run it. This is basically the code. It's really a minimal amount of lines, just a couple of functions that just encrypt data. We're getting a random 25-character key, and then 7. This is actually just returning 7 numbers. And so that's exactly what we're doing, is creating that artificially constrained key space that we're just going to brute force ourselves over. So high level, because I'm terrible at Visio, this is what you get. This is kind of how it works, is we just start at 1, and we'll try to decrypt whatever the code is inside. It'll decrypt and decode it. And then if that string basically matches what we expect, and so this is specifically for Perl, we'll have an encrypted string alongside the original code that we want to run. If this is what we expect it to be, then decrypt and inject our shellcode or run whatever our malware is that we want to. If it's not the key that we expect it to be and we cannot decrypt the string, it'll go back up and iterate down to the next value. So a quick demo of that is, so we have this hello world over here. We're basically just doing a printout. And so if no one can probably see that.
Just drag it over to
So if I do a brute force, give it the file hello world, and tell it to use Python, it's going to print out. So this is actually going to take a little while, so we'll go another key. All right, so here's a different key. So basically, it just writes out a file to disk, which is this encrypted.py. And so if you want to take a look at what that looks like, let's see if I can make this zoom in. Is basically right here is our encoded data, the original script, which is just that hello world. And basically right now we're just iterating over this range of, I think, it's 100,000 to 1 million. This is the original key down here. We're just appending that to that and then brute forcing and trying to decode and decrypt this script at runtime. So an example, if I command plus X encrypted, then we call it. This may take, 5-10 seconds at this point. We'll see. But right now it's going to be just iterating over the entire key space in the background. And then ideally, within a couple of seconds, we should see this program basically just print out hello world. The only thing to be aware of is obviously when you're doing something like this, it's going to take up a decent amount of processor, like runtime, essentially. So if you have a single processor system, which I don't know why you would anymore today, but you're going to spike your CPU usage. So here we go. In this case, it just printed out our code, which we're just printing out hello world essentially. And so you can apply this concept for any code that you've written. Right now we have Python, PowerShell, Perl, and C# is getting added in like within an hour or two. And we're finishing expanding this to other languages. I think this is you.
So let's talk a little bit more about building a profile about where you expect to run. We talked about profile. I didn't realize I was kind of cut off. We talked about profiles in that when you have a good idea of the domain you're on, you can learn things about the systems, and then you can target them even better. So that if it's running at company A, it won't even run at company B. Process names. If you want to go the Sandbox Detection route, you can look for specific process names like Wireshark, VMware, Process Explorer, etc. And if you see those on, you don't run. But if you want to go on a different route, if every computer on that domain has a certain process running, some sort of management tool, something like that, you can avoid that as well. You can say, this needs to be running as well. So here's an example in PowerShell. This is just a Sandbox Detection pure module where you look for all these different analysis tools, and you won't run if you find any of them. Windows updates is another one. Companies patch their systems at different rates. So if one of them has a certain amount of Windows updates, or there's a specific Windows update you're looking for, you can search for that before you run your payload. If there's a patch Windows applied that fixes some sort of vulnerability, well, you can check to see if that's there before actually executing and triggering all sorts of alarms. So here's an implementation in PowerShell again, looking for Microsoft Windows Update Client to see how many have been updated on that system. Registry size. If you want a computer that's more in use than others, then the registry is going to get bloated over time. That's just what happens in Windows. When you use your system a long time, you install things, the registry bubbles up, and it gets big. So this can be used as a fingerprint for the kind of system you're on, the company you're on. Check for a certain size of registry. And again, I'm just showing these in PowerShell, where we have them in every language, though. So now let's talk about user activity. There are a lot of reasons you want a user present besides just checking to see if you're in a sandbox. Number one, you might be auth to that system, but you don't have that user's credentials. So you could present a pop-up box that prompts them for their credentials. Number two, we've actually had success with this. We were running Cobalt Strike, and we didn't know how to get into the client's PCI environment. So what we did was we just set up VNC, we watched the user for a little bit, and we saw what sites he navigated to. And eventually we found a portal that led to their PCI environment, and that was just a little bit of watching. Another reason you might want a user present is because you have some two-factor system where you need them to be present and to click yes on a prompt. And that happens more often than you'd think in our experience. If you just ask a user to two-factor authenticate us, they'll just click yes without thinking twice. So Maskless is a good way to check if a user is present. If the mouse is registering clicks, they're probably there. So if you require a certain amount of clicks, your payload will just sit there until the user's back at his or her computer. And here's an implementation in Python. There's a import Win32 API. It's a good way of interacting with the kernels and all that, the kernel libraries. So you can get the key state, and you just keep iterating through this while loop, and you can just increment the count until the user is present. Here it is in PowerShell again, just a different implementation of the same concept. So this would be good in like PowerShell Empire or any PowerShell payload you have to just port this over if you want the user to be present. Mouse position is another way to check if the user is present. If the user's at their computer, they will be moving their mouse. It's a fact of life. So if you get the X and Y coordinates of the mouse at a certain point in time, you wait a little bit, you do like a long process, or you sleep, and you check again, then it should be in a different location. And if it's in a different location, the user's probably using that mouse to move around. And here is in Golang. You get the first X and Y coordinates, you sleep for a little bit, you check again, and you'll just print out, cursor hasn't moved, do not proceed, or the cursor has moved, the user's probably here, proceed. And Go, by the way, is a very neat way of interacting with Windows functions like core DLLs. You can just import a lazy DLL up there, and you can just reference all the functions with an unsafe pointer. Another one is just presenting a user with a pure pop-up box. And this is kind of one of my favorites, despite how simple it is. If they click OK on a box, that means they're there. That box can sit on their computer for days, hours, whatever. But when we have our code that presents this pop-up box, when they click it, we can execute. So here's how we implemented it in Ruby. Again, these accept command line parameters, so you can just pass in the title as the first argument and the message that you want to present in the next one. And we'll print at the end, now that the user has clicked OK or closed the box, we'll proceed with our payload. So this is a really effective way of figuring out if the user's at their computer or not. And here's a really bad GIF that I made. He's bad at Visio, I'm bad at GIFs, I guess. But this is in the PowerShell implementation. We present the title, security update. The message box will say, your system has been updated successfully. Here it is. When I clicked OK, the new line printed out that said, it's time to execute our payload. And you can customize that however you want for whatever engagement. If the client has some sort of software they use, you can say, hey, this encountered a problem. This software encountered a problem. Please click OK. There's a lot of other ways to secure your implants, and we went through a lot of them, and it took a long time, but there's so many more that we can and will implement. Here's just a few more. I encourage you all to check out the repository when you get a chance. And at this point, I'd like to say that we would really like contributions from the open source community, because we want this to be a centralized repo for everyone to add and pull from. So I'll get it merged in if you have any ideas you want to implement. And if you want to get practice with all these different languages, this is a good way to do it. Now Chris is going to talk about porting this to your payload, making it actually usable.
All right, so thanks, man.
Yep.
Finally, the way that we obviously went over a couple different random techniques. One may be effective in a certain environment, it also may not be. One thing that we like to think is you're not constrained, obviously, to just a single check either. A good way to look at this is if you're able to write your malware or your code to be exactly for the environment that you want, you can chain a lot of these different checks together to try to ensure that you're on the system that you're targeting or that you want to target and have your code run at that point. So in this case, there's a PowerShell implementation, it looks like, where it's just trying to pull the domain via a WMI query of the right here in this check. And so this is one thing that you can add, obviously, to PowerShell code. The next thing is, obviously, we're just starting to build on top of this. So we're now trying to say, okay, run on this domain, but if I'm not running under the context of this specific user account, don't execute this code, because I don't care about anyone except if a single user is running it. Another one is, with all of that said, only also run this malware or my code originally if I'm on a system or this specific system that I'm wanting to target. So if all of these basically chains don't hit, if one misses, then completely just ignore running my original code, become a calculator, do something fairly benign, and try to just sit there and have the program die. And so that's basically what we would do. So we start to build out, when we start writing malware for our assessments and try to move laterally, is we can do this. From a red team perspective, or our clients also really have seemed to like this as well, because one issue, if you're just writing generalized malware that's not doing specific targeting, if we hit a user at their home system, or if they're opening email anywhere basically outside of the domain, if it's non-targeted, then it likely is very possible that it could run. Obviously, we don't have the ability to just hack everything and hack anyone that we want to, so we have started to building in these constraints, limiting, again, like checking to validate that the workstation that our code is running on is joined to a domain and it's running under this user account. And our clients have actually started to see this and have actually preferred and started asking for that as we present it as an option. It takes a little bit more time, obviously, but it generally works out in the better for everyone anyways. So one thing is that this also provided a good opportunity to, I work on a tool, Veil, and doing something like this is pretty cool thing where I wanted to add this ability into Veil where we can start adding basic checks for payloads. And so we spent the time writing this, and actually I have a pull request right here. We'll go ahead and merge this in. And so what this will do is this will merge a ton of different checks from that we have from CheckPlease into Veil. And so this is immediately now available in case you guys are using Veil to start customizing your payloads. So we'll do a quick demo of what that looks like now. Do a poll. Assuming I have internet. There we go. All right. Oh, that didn't just work right there. Sublime. Sorry, one sec.
We're all familiar with the demo gods here.
Guy 175.
They're a fickle
We'll make
bunch.
this work. That's why. That one's not liking. All right. So we'll load Veil. Let's say we want to use just a Python payload, so we'll do this flat one. What flat means, by the way, is that there's no obfuscation, no encryption or anything added part of it. Obviously, you can see there's other payloads that are encrypted. The reason why flat payloads are released in the first place is in case anyone wants to figure out how to write malware in whatever language that you select. It's a baseline, so you can look at this, see, okay, I understand how shellcode is injecting or how I'm able to do these malicious actions, and provides the ability for anyone else to kind of take that and customize it and run with it to work for their environment. So let's go and use that. So now we have these different checks that are available. So we talked about, I like the user prompt, so set user prompt, we'll say true because we want to check for that. And let's do UTC times set UTC check true. So what this should do now is, so we have it set as true, it should prompt the user once we generate this payload, once it runs, and it should also check the system. In this case, what it's doing is validating that it's not, the system it's running on is not in the UTC time zone. So we can generate, let's generate shellcode real quick. All right, we'll do UTC prompt me now. We'll do a quick check to look at the source code so we can see that it's actually in here. All right. And if we look at the code, oops. So now what's happening in this case, we're going to be setting a title of system error in this value. This is just the basic dialog box that's going to pop up. We're calling message box W now. And then we're also performing a check right here where we're trying to pull the current time zone from the system and trying to validate, is this actually, is this not part of coordinated universal time? And as long as it's not, then basically run our malware underneath it. So let's make sure we have a handler going. So here now, we're running it. Okay, so we encountered an error. Please click OK. Click OK. And obviously, this is the only time we're going to be using something like this is if we want to actually validate someone is at the system before a code runs. So we can just click OK, doing a check, and right now this is going up, which is basically indicative of the interpreter DLL being loaded. And right here we have our session. So it's basics like this where you can start. So in this case, obviously, we only have 2 checks enabled. If I were to go through and enable 10 of them or 5 of them that are there for that Python payload, it would perform all of those checks. And if one misses, our code won't run. And that's kind of the way that we've preferred to start writing our payloads. And that's how we wanted to build this in. Okay. All right. We'll just go. I think at that point, that's actually it anyway. So The repo is available. It's under Brandon's GitHub page. It's under CheckPlease. Again, we have all these different pieces of code that are out there. It's just quick one-offs where we wanted to make it available. So if you want to add a single quick check, it's easy to do. You can also just chain one of them right after another. Add as many different checks in there as possible to customize your payload for your environment, and just basically, again, copy and paste code. And that's about it. If there's any questions, we'll take them. Otherwise, thanks.